1.4 Synopsis of chapters to follow. To begin, we consider the classical theory of point-particle motion and classical mechanics. This starts in section 2.1 with a brief description of Newton's calculus formulation, 1687, where the Newtonian force equals mass times acceleration, a second derivative on position in the notation of Leibniz. Leibniz was the other major inventor of calculus, with use of integral calculus in unpublished notes in 1675, and published in 1684, 4 translations see Struck. Leibniz also described the fundamental theorem of modern calculus, the inverse relation between integration and differentiation, in 1693. The early role of math-oriented polymaths in the development of the mathematical foundations of classical mechanics continued with Euler and Laplace. Euler made contributions early with Mechanica 1736, but continued with developments in the underlying mathematics and mathematical physics for several decades, impacting Lagrange more than 50 years later in 1788 with the synthesis known as the Euler-Lagrange equations. Laplace's method described in 1774, similarly, had a major impact on Hamilton's reformulation in 1834, which gives rise to the classical propagator associated with the integral from 2 of e raised to the mf of x power dx for m is much greater than 1, as well as path integral methods in the 1940s, quantum propagator associated with the integral from 2 of e raised to the imf of x power dxm is much greater than 1.
After Newton, the next major formulation of the classical theory was with D'Alembert's description of force in the context of virtual work, 1743. Virtual work, balancing to zero work actually done, is equivalent to a form of the Euler-Lagrange equations, which reacquire the equations of motion as before but now with a much easier description of holonomic constraints, such as for rigid bodies, where constraint equation is not a differential equation. In section 3.3.1 we review the types of constraints, such as holonomic. In many situations we have non-holonomic constraints, such as for a rolling object. The complication of non-holonomic constraints is easily managed in Hamilton's reformulation in terms of the principle of least action, 1833-1834, described in Chapter 3. Hamilton shifts the mathematical underpinning of the theoretical formulation to be a variational extremum of an action functional defined as the integral of a Lagrangian function for a point particle over time, along a trajectory or path. The variational minimum, e.g. the least action principle, then recovers the Euler-Lagrange equations to describe the same equations of motion as with D'Alembert, except now we have the means to handle non-holonomic constraints by way of Lagrange multipliers, briefly described in section 3.3.1, and then used in some examples in section 3.3.2. Hamilton also co-discovered quaternions, 1843-1850, along with Allen Rodriguez, 1840, which would be used in expressing early electromagnetism by Maxwell, to be discussed in reference 40, and in indicating more complex algebras, a prelude to quantum mechanics to be discussed in reference 42.
The variational formulation shown in Chapter 3 also unifies the classical theory in other ways, as well as bridging to the new quantum theory, details in reference 42. This is because the quantum theory can be expressed in terms of an oscillatory integral formulation, where the constraint to have a minimal action is arrived at not as a fundamental variational rule, but as a consequence of summing over all paths of motion whose actions enter as phase terms in a highly oscillatory integral, initial math development from Laplace's method, that in turn selects the classical equations of motion as a zeroth-order approximation to the oscillatory integral. Stationary phase. At first order we have semi-classical effects, and a sum of the full quantum description gives the full quantum theory. See reference 42 for further details. Chapter 3 specifically explores the application of the minimal action formulation in terms of a functional, the action, on the Lagrangian function integrated along a specified path. A wide range of classical systems can be described with such an application of the variational methodology. There are two main ways to formulate the action functional that are related by Legendre transformation: 1. The aforementioned Lagrangian method, and 2. The Hamiltonian method. The Hamiltonian, to be described with applications in Chapter 6, is associated with conserved quantities of the system, if they exist, such as the energy. In this latter sense of describing the conserved quantities of the system, the Hamiltonian is introduced in Chapter 3, to express those conserved quantities in the solutions. The analysis from the perspective of a full Hamiltonian variational analysis, however, is not done until Chapter 6. The intervening very brief sections include Chapter 4 Classical Measurement and Chapter 5 Collective Motion.
Chapter S3, 6, and 8 describe the first-order Hamiltonian formulation in terms of canonical coordinates. The phase space representation of the system dynamics in terms of the canonical coordinates then allows the properties of the Hamiltonian to be explored when seen as a mapping function on a phase space. We find that such mappings are area-conserving and allow us to describe the asymptotic system behavior with ease in many situations, including situations that clearly demonstrate a radically new phenomenon, chaos. The ubiquitous occurrence of chaos, and of classical systems, at the edge of chaos, is then described in Chapter 7. The universality of chaos was shown in Feigenbaum's 1976 paper. This universality occurs with the assumption that the mapping function has a quadratic, parabolic, local maximum. Feigenbaum indicates this as a normal relation but does not elaborate further. It turns out that having a quadratic form for the local maximum, near a critical point, is a general property from the calculus of variations and Hilbert spaces known as the Morspieler lemma. The assumption underpinning the universality of chaos is valid if there exists a smooth enough function near critical points of interest, e.g., that there exists a manifold description with a smooth function. Suppose we turn this on its head, as will be done in reference 47, and suppose that chaos is a fundamental limit, always present. If this is true, then Morspieler must always be applicable, thus we have a manifold geometry. This is interesting because before we even get to dynamic fields/geometries, manifolds, in reference 41 we see evidence of such a mathematical construct existing as a consequence of the universality of, universality.
Chapter 8 goes into more explicit properties of canonical coordinates and transformations between them. This allows canonical coordinates to be chosen that greatly simplify the analysis by decoupling the equations of motion and making them constants of the motion, or coordinates of the motion, in many cases. The most decoupled case is described by what is known as the Hamilton-Jacobi equation, which, when shifted to the operator formalism for the quantum theory, described in reference 42, becomes the familiar Schrödinger equation. Another formulation, in terms of appropriately chosen canonical variables, gives rise to the Poisson bracket formulation. This is also discussed not for its application in classical physics per se, but due to its trivial shift to an operator-commutator formulation to arrive at the first quantum reformulation of the classical theory, the Heisenberg formulation. Chapter 9 continues with another advantage of the Hamiltonian formulation, a conserved quantity in many systems, via its application to perturbation theory. The use of Hamiltonians in both classical and quantum perturbation contexts are discussed. Chapter 9 also describes dimensional analysis, which when taken together with an analysis of conserved quantities, can give rise to surprising solutions based on self-similarity alone, with a few classic examples given. Extra exercises are placed in Chapter 10.
The classical mechanics described in this book only briefly touches on special relativistic corrections, i.e., it is focused on particulate matter moving at non-relativistic speeds. Thus, in this book there is the approximation of absolute time, a notion of simultaneity, and of instantaneous transmission of force with changing source position. Note that this separation of special relativity from the classical physics of this book is also reasonable, physically, in that at the level of particulate, non-relativistic, matter examined there is little opportunity to see special relativistic effects. See section 3.3.2 for an early experimental indication of the existence of a 4-vector magnitude for energy momentum in the Compton scattering formula. Another example where relativistic effects were seen, although not realized at the time, was in the experiments of Fizeau on light propagation through flowing water, 1851. Einstein remarked that the experimental results which had influenced him most were the observations of stellar aberration and Fizeau's measurements on the speed of light in moving water. The Fizeau experiment, section 4.3, gives rise to a relativistic velocity 4-vector addition calculation for the relativistic Doppler effect. Once the relativistic Doppler effect is revealed, all of special relativity can be recovered by means of the Bond decay calculus, described in reference 40. Once we get to notions of dynamical force fields in reference 40, the Lorentz transformation on Maxwell's equations, as four vectors, is revealed. 1899. An extension of these transformations to all matter, a law Einstein then follows in 1905. For this reason, the theory of special relativity and background and problem solutions are placed in reference 40 on fields.
Thus, the fields described in this book, if at all, are static or stationary, where discussion of their general dynamical role is deferred to. The classical mechanical systems considered are also simple in that only a few elements are interacting and in motion at any given time. The connections to systems with many elements is mainly left to on statistical mechanics. Even at the classical mechanics level, however, we can still see preliminary signs of new phenomena, due to emergent martingale phenomena and law of large numbers (LLN) behavior. From this we can begin to see that there are new fundamental parameters, such as entropy, discussed in reference 41, in regards to information geometry, and in Book 6 on statistical mechanics. Note that before we arrive at reference 44 on statistical mechanics, where the fundamental role of entropy is mainly explored, we will have already discovered entropy in the context of the statistical learning theory on a neuromanifold, given in reference 41. When statistical learning is performed on a neural net, NN, construction with NN learning via expectation/maximization, the learning process can be described using information geometry. Information geometry is a differential geometry formalism applied to families of distributions in statistical learning processes. In optimal statistical learning, it can be shown that entropy is selected for local notions of distributional distance in a similar process to Euclidean distance, flat spacetime, being selected as a local geometric notion of manifold distance. In this way, entropy is singled out as a local measure just as locally flat spacetime is selected, with local Minkowski metric. Aside from the theory connection, direct implementation of statistical learning, in the form of AI-based SVM learning, is actually an exercise in Lagrangian optimization with non-holonomic inequality constraints, see reference 24, so will be directly accessible to those that have mastered the material in this book.
Now to begin, with Newton.